The special theory of relativity, or special relativity for short, is a scientific theory of the relationship between space and time. It is an explanation of how speed affects mass, time, and space. This theory includes a way for the speed of light to define the relationship between energy and matter. Relativity theorem is formulated by Albert Einstein, which states that space and time are relative and all motion must be relative to a frame of reference. In this video, involving the relativity of length, we will be deriving a formula of the given task problem and try to solve it. But before we would proceed, let's first get familiar with the special theory of relativity, the relativity of length or length contraction.
According to the special theory of relativity, length contraction is a phenomenon that a moving object's length is measured to be shorter than the proper length, which is the length as measured in the object's own rest frame. This contraction is usually only noticeable at a substantial fraction of the speed of light. Length contraction, L, is a shortening of the measured length of an object moving relative to the observer's frame. This would be the formula of the length contraction. If we measure the length of anything moving relative to our own frame, we find its length L to be smaller than the proper length LO that would be measured if the object were stationary. For example, if the moon's reference frame, the distance between the points where it was produced and where it decayed is shorter. Those points are fixed relative to the Earth but moving relative to the moon. Clouds and other objects are also contracted along the direction of the motion in the moon's reference frame. Now, let's use this to solve the given problem.
A spaceship flies past Earth at speed of 0.99 c. A crew member on board the spaceship measures its length, obtaining the value of 400 meters. What length do observers measure on Earth?
We know that this problem is relativistic. We could assume that this is not equal to 400 but less than 400. So, how much exactly is it? By using the formula of length, construction L or the measured length is equal to the proper length LO times the square root of 1 minus u squared over c squared. Now that we have identified the formula, now we could proceed to substituting and solving.
The measured length is equal to the data from the crew members inside the moving frame, which we could now identify as its proper length as 400 meters, times 1 minus the observer from Earth, which has a different number of speed of u or light. Because of the endpoints or between the two events of the moving frame, which were given as 0.99 c, then squared over c squared. In squaring this one, we'd have to distribute the lowest exponent, so 0.99 squared and c squared will be cancelled out. Now, we have 1 minus 0.99 squared, then square root and multiply it by 400. The answer would be 56.4 meters.
We could conclude that if the spaceship is 400 according to the observer inside, the observer on Earth measures only 56.4 meters. This is how the relativistic length contraction according to special theory of relativity works.
I hope you had learned something from us from this video.